Good morning, students. Today we are going to discuss about magnetism and matter. It is very interesting chapter, and in this chapter we will study about the magnetism of earth, the basic property of the magnet. In the previous chapter you studied that when a current flows through the wire, then it develops magnetic field around it. We applied Biot-Savart law for calculating the magnetic field for the various shapes of the wire and at the different points. Now, here we will study about the magnetism in the matter itself, not by the current carrying conductor. Hence, the word magnetism first of all comes out from the word Magnesia. Magnesia is an island in Greece. The rocks on the island Greece has a property to attract the metal, to attract the iron, and the villagers of the Greece of the island Magnesia found that their shoes were stuck up with the stones present on the island. Means that stone has a property to attract the iron pieces which are present in the shoes. Hence, the word magnet comes out from the Magnesia. Natural occurring iron ore are called magnetite, and later on the magnet comes from the ore. That ore is called magnetite, and this also known as lodestone. This is also known as lodestone. Next property, when piece of iron is rubbed with magnet, it acquires attractive and directive property, and this is called artificial magnet. For example, if this is an iron nail, if you will rub this iron nail by the magnet like this, again and again, like this, again and again, then this nail has a property, that is, property will develop in this nail that it can attract small pieces of iron. Therefore, this is called artificial magnet. Artificial magnets can be demagnetized by heating, hammering, or by throwing. Artificial magnets from soft iron or steel, they are made of either from soft iron or by steel. So, the magnet which are made from soft iron, they can be magnetized easily, soft iron, but they can be demagnetized also. They can be demagnetized very easily, very rapidly, but steel takes time to demagnetize it. So, generally we prefer for the different uses either steel or soft iron. And the magnets may be of different shape. It may be like bar magnet. Bar magnet, for example, this is our bar magnet. See, there is a dot over here. This dot represents the North Pole. So, the shape is like a bar magnet. It may be in shape of U, or that is called U-shaped magnet. So, as per the need, we have the different shape like bar magnet, U-shaped magnet, etc. Now, students, bar magnet. It is a very simple magnet. See, This is a bar magnet. Point indicates north, the other end indicates south. It is like this. This is a bar magnet. See the cross section. And the properties related with this bar magnet, very interesting. First of all, bar magnet has a property of attraction. That is, it can attract small pieces of iron. For example, this is an iron nail. See, it has a property of attraction from this end as well as from this end. The iron nail gets attracted by the bar magnet. Second, property of alignment means if you suspend this bar magnet freely, then this bar magnet, if for example this is our geographical north and this is geographical south, then bar magnet always align itself along this direction, north-south direction. The north of the magnet always towards the geographical north and the south of the magnet always towards the geographical south, like this. This bar magnet, this is the north and this magnet always align like this. Therefore, it has the property of alignment. Next, like pole of the magnet always repel each other. For attraction and repulsion of the magnets, for example, this is a magnet. This black part represents north pole of this magnet. This is also a magnet having the black part, north pole. Now I place this one magnet over here in this small test tube. North pole is towards upward direction, and if I will put like this, that is north pole is towards downward direction, then see what will happen. Does this upper magnet falls towards downward direction? No, it stops. This is the north pole, this is also the north pole. These two same poles are there, so there will be force of repulsion. On the other hand, if for example this is one magnet, north pole is in the upward direction, see, if I will put the magnet, second magnet in this direction where south pole is in the downward direction, see, there is an attraction. That's why the poles having or you can say like poles always repel each other and unlike pole always attracts each other. Next is property of pair. What is the meaning of property of the pair? Property of the pair means that this is the north pole, this is the south pole. It always, for a magnet, there must be north and south pole. If you will cut it into the two halves, then what happens? If you will cut it, again this end is south, again north will develop, another south will develop, and this is north already. That is, if this is the complete magnet, north and south, if you will cut it in the two halves like this, if this is one half, this is another half, then this north and this south is already exist. These two halves, the surfaces of these two halves, this end becomes south and this end becomes north. That is, again automatically north and south will develop. That is, magnetic monopole will not exist. Monopole means it is not possible that north pole exists separately without south pole. So always for a magnet, north and south poles are there. Now students, we will study about magnetic field and magnetic field lines. What is magnetic field? If this is a magnet, then a region will develop around this magnet. And what is a special property of this region? If you will put any magnet within this region, then this magnet experiences some force like this. For example, this is a magnet, and if you will bring, see at present, see the deflection. Now if I will bring this compass needle within this magnetic field, see what will happen. It experiences, the needle, compass needle experiences some force. So this shows that there is some region around the magnet, and this region is called magnetic field. Now how can you represent the magnetic field? Magnetic field is there around the magnet, or it may be around the straight, or maybe of any shape current carrying conductor, which you studied in the previous chapter, that current carrying conductor develops a certain magnetic field around it. So that particular field is called the magnetic field. Field lines are the imaginary lines, and the tangent at that point is the direction of the magnetic field. There are different types of magnetic field. First of all, uniform magnetic field. What is it meaning of uniform magnetic field? These are the representation of uniform, that is, all the field lines are parallel to each other. See, they are parallel to each other. So this represents uniform magnetic field. If you will make a cross, all crosses are at the equal distance, that is, field lines are entering into the board. If it is dot, means field lines are coming out, and all the dots are at the equal distances. So all these represents uniform magnetic field. On the other hand, see that magnetic field, does the magnetic field intensity over here and the magnetic field intensity over here is same? No. Number of field lines which are passing through this particular area, it is different. So this is non-uniform magnetic field. If this is a bar magnet and it is a north pole, this is the south pole, then see, magnetic field lines comes out from the north and they ends at the south like this. And remember, outside they comes out from the north and ends at south, but again they move within the magnet like this. That is, they are moving, field lines are moving from south to north. Again, if you will draw the magnetic field line again like this may be like this. Like this. So if you will draw complete diagram of this magnetic field, you will get like this. So this is the magnetic field line, this is another magnetic field line, this is another. Now this magnetic field line will go like this, and again it comes over here and ends over here, and this forms like this. Like this. Again this magnetic field line will go like this, and finally it ends over here, ends at south, and again from south to north like this. So all this magnetic field line will comes out from here and ends over here. So all these are the magnetic field lines. Now as far as the properties of the magnetic field lines are concerned, first of all, see, first property of magnetic field line, properties of magnetic field lines. First, what is the property? They always originates from the north and ends at the south. Originate, or you can say they always comes out from outside the magnet, they always comes out from the north. That is, magnetic field lines always comes out from north, and ends at south pole. Second property, these magnetic field lines are the closed curves. See, if you will select this magnetic field line, it originates from the north, ends at the south, again within the magnet it moves from the south to north. That is, this forms a complete closed curve. Magnetic field lines always closed curve. They always closed curve. This is only the distinguished property between the electric field lines and magnetic field lines. Electric field lines never acts, they are not closed curves. They originate from the positive, ends at the negative, while here they all comes out from the north, ends at the south, but within the magnet they moves from south to north. They forms a closed loop. That's why magnetic field lines are always acts as a closed curve. Third property, tangent at any point. If you will draw the tangent, suppose you have selected the point P on the magnetic field line. Draw the tangent. This direction of the tangent gives the direction of the magnetic field at that particular point. So, the direction of tangent gives direction of magnetic field line, magnetic field intensity, gives the direction of magnetic field intensity. Now the next property, that the magnetic field lines never intersect each other. See, is any two lines, magnetic field lines, they are intersecting? No. That is, magnetic field lines never intersect. They never intersect. Why? Because if they intersect, this is the position. Now, at this point P, if you will draw the tangent of this curve, this is like this. If you will draw the tangent at the point, same point, due to this curve, the tangent is like this. So, the point P experiences force in two different directions. It means the magnetic field has two different directions at a particular point. Is it possible? No. Therefore, the magnetic field lines never crosses each other. Next point, fifth, they always originates perpendicularly. See, they are originating perpendicularly. All magnetic field lines are originating perpendicularly. See, it is not possible that if this is a magnet, north and south, these are the magnetic field lines. No, it is not so. Magnetic field lines are not perpendicular at present. Therefore, it is not possible. See, all the field lines, they are originating perpendicularly and ends perpendicularly. You can see this magnetic field line. This makes 90-degree angle and this makes also 90-degree. They originates perpendicularly and ends perpendicularly. Originates and ends perpendicularly. So these are few properties of magnetic field lines. Now you can note the content. Our next topic is magnetic dipole. As the name indicates, magnetic dipole. In the first chapter you studied, students, about the electric dipole, where the two charges of equal in magnitude but opposite in polarities are separated by a certain distance, and this forms electric dipole. The same concept is over here. The difference is that instead of electric dipoles, here we have magnetic dipoles. Means magnetic dipole means two poles N and S, and these two poles are, for example, of bar magnet, and these two poles are of equal in magnitude, but one is north and another is south. Now these two poles of pole strength Qm, the same pole strength is of south also, Qm, means Qm means magnetic pole, strength of magnetic pole. The polarity is different, one is north, another is south. Let these two magnetic poles are separated by a distance 2L. See, that is from the center it is L, this is also L. So the dipole moment which is the dipole moment of the magnetic dipole. So you can say, you can write it as magnetic dipole moment, which is represented by M. This is the product of any charge in the electric dipole. That was electric charge. Here in magnetic dipole, it is the product of any strength of the pole, and any strength of the pole, here it is Qm, and the distance between the two poles, it is 2L. So this is the magnetic dipole moment M. Now the pole strength has unit ampere meter into, it is a length, it is also meter, that is ampere meter square is the unit of magnetic dipole moment. And remember, direction of magnetic dipole moment is always from south pole to north pole. Direction is always from south to north. This is the direction of magnetic dipole moment. In the electric dipole moment, it was represented by P. Here magnetic dipole moment is represented by small m. In continuation of the previous article, magnetic dipole, for example, students, if this is a magnet and north and south pole is here, 2L is the length, Qm is the pole strength of this magnet. Now first, if you will cut this magnet along the length, if you will cut this magnet along the length, If we will cut it, then the shape will be like this. This is one piece and this will be another piece. That is, this 2L length will remain same. Along the length 2L will remain same, but the at present pole strength of this N and S, pole strength will be Qm upon 2. So, the magnetic dipole moment M reduces to half. See, Qm into 2L, here Qm by 2 into 2L. Magnetic dipole moment reduces to half. In second case, if we will cut the magnet vertically, what happens? This is a magnet. If we will cut it into the two halves like this, this is one half, this is another half. So what is the length of this one part? Length of the one part is L, another part is also L. The pole strength will remain Qm. Now the pole strength will remain Qm, but the length reduces to half. So our magnetic dipole moment M, here it will be Qm into L for the one part. It has L. Therefore, again see, this M dash reduces to half.